So we have the central limit theorem telling us that no matter what type of population distribution we have, when we sample repeatedly, we're going to get a normal distribution. Just this morning, I went ahead and added a playlist by 3 Blue 1 Brown to our WebLinks module. And it's 4 videos. The first one is all about the central limit theorem and then why things happen in the normal distribution the way they do. But that first one really shows us completely, no matter what distribution we have. I recommend taking a little while to watch that one. But once we have that, I can then say, how do we address some of the other issues we were looking at for our minimum variance unbiased estimators? So when I have such an estimator, like X bar for mu, I can say, all right, I went ahead and I calculated my sample average. And I use this to estimate mu. But then I said, we should be able to say, all right, if I knew mu, where would the sample average lie? How confident am I that those two are close together? We get to decide how confident we want to be. Remember, we said that was something we could control when we described this on Friday. So if I knew the population parameters, since I was doing a normal distribution, I could say, well, how close is close enough? How big a range do you have to be sure your sample mean is in there? Okay, wait a minute. How am I going to figure out what's reasonable? So here's where you get to make a decision. You get to decide, do you want to be 90% sure we're in here? 95% sure? 99% sure? How sure do you want to be that we're in here? Now, what do I mean by how sure? Well, remember the picture for our normal distribution, right? Our standard normal distribution is that bell curve we've been using this whole time. If I say I want to be 90% sure that this number is close enough, that means I want to throw out 10%. I'm going to come up with two edges, aren't I? An edge on the left and an edge on the right. And I'm going to be able to say, oh, we should be bigger than this number and smaller than this number. And then the area in the middle. The area in the middle of my normal curve should be 90%. Oh, wait a second. If I'm looking at a normal distribution, and I want this to be 90%, I can find a z here, can't I? Grab table C1 or C2 out of the back of the textbook, or grab your calculator, and we're going to use the normal distribution piece in there. I want to know how to get that z. Now, only part of this is on the table. Part of it is still stuff I need to do with this picture. The 90% in the middle. How much is up here? 5% is there, and 5% is there, right? So that means that this half of that middle section is what? It's 0.45. Okay, if that's got an area of 0.45, you can look up in table C1 what area is 0.45 and then get a z value that goes with it. We're inverting our normal distribution. We're finding the z from the area. So I say to myself, 0.45. And I remember having this discussion on Friday. I said, oh, that's right between these two. So those are the columns for 1.6 between 4 and 5. I'll call it exactly halfway between 1.645. And so I can say, oh, the z value is 1.645. So I can define an interval for my sample mean. When I do this, my sample mean should be between mu minus 1.645 times the standard deviation. But it's the standard deviation for the sample mean. That's my standard error. The standard error came from the standard deviation from the original population. There was a formula we did on Friday. Anybody remember what that one was?
the sigma over square root of n.
Now that choice of 1.645 is based on my decision for my precision. I'm 90% sure that my sample mean will be in here. What if I want to change that level of precision? Let's say instead of 90%, I want it to be 95%. See those both at the same time there. How's this going to change if I want to move that number from 90% to 95%? I got to go back and I got to look at this Z thing again. And I got to figure out what the appropriate Z value is instead of 1.645. Now, I'm going to draw the same picture. And I'm going to say, oh, the middle is now 95% instead of 90%. Same picture. Different number in the middle. So I ask the same question. What's this little tail here? And that means that this piece is or 0.4750 in area, right? Find me 0.4750 in table C1, or we can use the graphing calculators for the inverse normal idea. Now, if I'm doing the inverse normal operates off the cumulative distribution function, which means I don't need 0.475. I need what number?
0.9.
Because I have to take all of the stuff on the left. And again, my distributions live here under the variables button, second distribution, there's an inverse normal. Oh, I want 0.975. One 1.9, I'm going to go with 1.96. Lo and behold, in our standard normal distribution, in table C1, 0.475 is the one in the box. That's how often we use this one. And 1.96. That's the one that gets used the most often. We use that number a lot. But I have the 1.65 from back here. I have the 1.96 now. And if I want 99% confidence, then I'm going to have to keep looking for what number in my table? I'm a very visual person. My immediate reaction is to redraw that picture and relabel it so I know the number to look for. Whether I'm going to use the inverse normal on the calculator or the table to find that number, I need to know what number I'm looking for. So what's the A value for this percentage? Ah, so this is 1% on both sides, which means this is 0.5% up here, which means my shaded area is 0.4950. I went ahead and did that here. That meant I needed 0.995 to get everything to the left. Oh, 2.576. And you can adjust these numbers for whatever level of precision you want. All three of the numbers we just came up with appear in our textbook. At the bottom of page 279, it shows a 90% interval, a 95% interval, and a 99% interval. But rather than just throw these numbers at you and say, hey, memorize these, I don't care what the percentage confidence is, I can do it by looking it up on that same table. Notice that when I say, oh, you did a sample mean, I want to be 90% confident, I get a smaller interval than when I want to be 99% confident. If I want to be 99% sure it's in here, I have to make that wider, then I'll only be 90% confident. So the higher my confidence, the larger this number gets, because we want to be more sure, we need to take larger and larger room. So if I tell you we have a population mean of 100, a standard deviation of 12, a sample size of 36, I would like a 90% interval for sample mean. What's the low end of my interval? What's the high end of my interval? What's the first thing I need to change to get the answer here? Mike?
First thing I.
And the z-score for 90% is? Okay. Now, I need to add or subtract from my average 1.645 times something. What goes in that set of parentheses? Because I need to change the standard deviation to the standard error. And that means dividing by the square root of my sample size. Square root of 36, though, is 6, which divides nicely here. So I just have to add 2 times 1.645 and subtract. So I get, when I subtract the low end, what'd you get?
96.71.
When I add,
3.29.
ta-da! If you wanted to be 95% confident, or create a 95% sample interval, you use a different z-value. 99%, you use a different z-value. 98%, it depends on what you're looking for. Questions? At the top of page 280, our textbook does this exact calculation for the GMAT scores that we were talking about on Friday. So you can get an example where we already knew the exact population mean, we already knew the population standard deviation, and you can come up with exactly that answer. Now, what is important to remember is the difference here between using the standard error and using the actual standard deviation. When you are dealing with an interval for the mean, you must adjust by the sample size. If you're just looking at a sample, then you don't. You would add or subtract the original standard deviation. Only when you're averaging. Questions? Come on, people, talk to me. Probably none of you are asking this, but personally, I think this is asked backwards. Because if I already know the entire population mean, why am I sampling? If I already know the entire population standard deviation, why am I sampling? I think it is far more common to do this the other way around. To create confidence intervals for the parameter. Now, there are two different ways to do this. The first one requires me to know the standard deviation for the whole population. Now, there are times when I will know the standard deviation for the whole population, like I know something about the process we are doing. we talked at one point about filling bottles in the last chapter as an example of a process where I could say, oh, the whole line has a standard deviation of, I don't know, 5 milliliters filling this 400 milliliter bottle. But I can now say, oh, I don't know the average all across the whole thing, but I take a sample and I say, all right, how's this set of bottles compare? In this case, I'm going to do exactly the same calculation with mu and x bar reversed. Now this z is based on how confident we want to be that our sample gave us a good reading on the whole thing. Remember, now I'm saying I don't know what the actual average GMAT score is, but I know this group had an average of 518. How close is that? How sure am I that the real average is somewhere in here? Based on my confidence level, confidence level is a big percentage, right? 90%, 100%, whatever it is, right? It's 89, what did we did 90 and 95 and 99. I don't think I can do 100%. We'll leave that one out. 90, 95, and 99. I'm going to call this number 1 minus alpha. Why 1 minus alpha? Because I think of that as the area in the middle and alpha as the area on the outside edge. If this middle area is 1, oh, don't show you the picture, it's not going to help. If that middle area is 1 minus alpha, how much is on the outside? On each side separately. For this case, but in general, this is going to be half of alpha, right? Half of alpha will be at the top on the right side, half of it will be on the left side. In this case, it'll be 0.05 and 0.05, right? We're going to call this Z alpha over 2 for exactly that reason. So I'm going to rewrite my formula and I'm going to say, oh, my confidence interval is going to come out of I said it and then I wrote it down the wrong way. Remember I said we were going to reverse mu and x bar? That means I need to put the x bar here. Oh, I got my sample. I'm only doing it for this one. In the previous one, it was mu. For this one, it's x bar. Just rearranged. This is the new idea. So now I have mu is in the interval from x bar minus z alpha over 2 times the standard error and x bar plus Z alpha over 2 times the standard error. That's a closed interval. Max, if I'm doing 90%, then that's Z.05. But we just figured out what that number was. What was that number? Right. And if we did a 95%, then Z 0.025. And if we did a 99%, that's Z of 0.005. What were these numbers? And 95? 1.96. But now what I'm doing is I'm saying, oh, I got this estimate, X bar. I calculated that myself. The real average should be in here. The population average that I don't know should be in this range. And what I've really done is I've answered the question, what's the probability of being in here? That goes all the way back to chapter 5. Basically, what we did in all of chapter 7 in this homework you've just given me is we looked at the distribution. We said, what's the chance of being in this part of the distribution, in this part of the distribution, whatever area we shaded in, right? Well, now the area I'm shading in is this middle section. The chance of being in this interval is 90% when I use 1.645. It's 95% when I use 1.96. It's 99% when I use 2.576. So what we're doing is we're turning around our probability question. I'm saying, oh, I think the answer should be here. I'm 90% sure it's in this section. When I have a normal population, as long as I'm sampling with a large enough sample size, we can make that assumption. We'll figure out ways to check later. But I can now say, oh, I'm 90% confident the correct mean is in here. 99% confident it's in here. When you go and look at a graph in a business report, you'll see these error bars. Those error bars are these intervals above or below your average calculation point, the point you put on that scatter plot, has those error bars created from here. Page 284 doesn't even give me a setting at the moment, but it tells me in problem number 11, it tells me we have a calculated average of 2.4. We have a standard deviation of 0.15. We took a sample size of 9. I would like you to form 3 different confidence intervals. A 90%, a 95%, and a 99%. I'm going to abbreviate confidence interval with the letters CI frequently. I just want you to know that's what that stands for. But the first thing I need to do before I do a confidence interval to make my life easier is to do what Mike did for us last time. We need to calculate the standard error instead of just using the standard deviation. So since I'm working with a sample, I need standard deviation of the mean, the standard error. What do I get here? And now I can use each of the appropriate Z values to come up with my confidence intervals. To do a 90% confidence interval, I'm going to do 2.4 minus the Z value, 1.645 times the standard error. And then I'm going to do 2.4 plus 1.645 times the standard error. And that's the lower end and the upper end of my confidence interval. Now, here is where I'm going to be a little pedantic, and I'm just going to keep all the freaking decimal places. But were I a lab science person, I would say none of these numbers have more than 2 significant digits. I shouldn't use more than 2 significant digits. I'm not a lab science person. And if I round to 2 digits, I'm not going to get very much information here. Because when I do this multiplication, what do you get when you multiply those two? Which if I only rounded to 1 decimal, to 2 digits here, would be 2, 4, and then 08, right? It would be 2, 4 minus, I'm going to lose some information. Notice that still requires me 1 more decimal place in the answer than I had in the information above. Me, I'm a math person. Keep all the freaking decimal places and round off at the end. So I end up with 2.31775 and 2.48225. And now I can make a decision on where I want to round. I would always go at least 1 more significant digit than was given in the original. So I would go with 232 and 248 if it were my data. Depending on your source, you might be asked to do different things. What changes for 95% confidence interval? Exactly. Instead of 1.645, I use 1.960. And to do a 99, I'll use 2.57576 instead. As our percentage of confidence gets larger, our interval gets wider. When I do the 95% confidence interval, (2.4 minus 1.960 times 0.05, 2.4 plus 1.960 times 0.05. I end up with, as my low number, 2.302. With my high number, 2.498. Not a huge amount wider, but clearly wider, like from 0.48 to 0.498. It got bigger. Right. Last, but by no means least, give me the 99% confidence interval.
2.2712 higher is 2.5288.
2 point,
Oh, 2712,
and then
2.5288.
wider still. Why? Seriously, who gives a? Okay. How many going to come? How good is the shape it's in? Do you keep track of your mileage? Why, Max? Why do you keep track of your mileage? That was actually what I referred to. Why do you calculate your gas mileage? What benefit is that to you personally?
Well, let's see, like, how much money you get per gallon, then looking at that. So,
Aha. You get a number from the car manufacturer. And then you go out and start driving, go, all right, am I even close? Did they lie their asses off to me? They gave you what they said was the population average. Your average miles per gallon should be. Then you go out and start driving, you're like, wait a minute. How reasonable was their estimate? This is something that has been a subject of quite a bit of debate with the rise of electric vehicles that don't have gas mileage. You get miles per gallon equivalent in an electric car. And it says, all right, we expect if this is how much a gallon of gas costs, this is how much this car's electricity would match out, this is what fuel efficiency you should get.
Yeah, 'cause I don't know.
See, hybrids do the same thing, and they jack up the mileage because they're looking at two different options, right? Are you doing highway driving versus city driving and all of those, and then they say, well, what's right? By the way, the reason I keep track of my mileage is it's the first indicator that something's going wrong. Before the idiot light shows up on the dashboard and says, hey, you should go get this looked at, my mileage drops about 5 or 6 miles per gallon. My gosh, something's going on. Problem number 15. Combined city highway gas mileage of a 2023 Lexus hybrid is normally distributed with a known standard deviation of 0.33 miles per gallon. If a sample of 10 trips yields an average of 41.5 miles per gallon, what is a 95% confidence interval for the actual miles per gallon? 95% confidence interval for the actual average. Now that said, we took how many trips? Okay, I should write that down because I need that number. Why do I need that number? Because that is N. That's going to help me find my standard error. Now I said we did that first. We did it previously as a separate calculation. We took the 0.15 divided by the square root of 9. I can do it in one fell swoop if I want. I can say, oh, the 95% confidence interval should take X bar minus the right z times the known standard deviation divide, that should be an n, to get the standard error. So here's a version with no numbers in it. That formula works every time. So I don't actually have to do the standard error separately. I can do it at the same time. So now I get 41.5 minus, I'm doing a 95% interval.
1.96.
Exactly. And then 0.33 over the square root of 10. And then the same thing with a plus sign in the middle. 41.5 plus 1.960, 0.33 over the square root of 10. Now I just grab my calculator and figure out what this number is that I am adding and subtracting. 1.96 times 0.33 divided by the square root of 10. I'm going to add that to 41.5. I'm going to subtract that from 41.5. So 41.5 minus that number. That's my low end. Go ahead. Okay. And then recalculate the number and add 41.5. 41.705. So my actual stickered mileage should be somewhere in that range. And if it isn't, then something was either wrong with their number or something is wrong with my car. And I need to know. There is one other question. What happens when I don't know this number? If I don't know the standard deviation, what am I going to do? That is what we will discuss on Friday, because on Wednesday, we'll have the exam. I will post the key to this homework. There is a note about the exam itself. You are permitted the use of a formula sheet, one side of 1 8.5 by 11 sheet of paper. Only thing that should be on the back should be your name. On this, formulas, definitions, no worked out examples. Some of the things you should know how to do are written in that note. So if you have questions, come see me tomorrow or this afternoon, or email me or something like that. And I will see you on Wednesday for the exam.